Scene 1, Deconstructing to the Core. Welcome to the 9th lecture of our series on wave mechanics. In previous lectures, we demolished the half-century-old impedance matching theory of microwave absorption. Today, we reveal the real physical mechanism of microwave absorption in film, as published in our papers in Materials Chemistry and Physics in 2022. The standard reflection loss formula is mathematically derived from the superposition of an infinite number of back-and-forth reflections. However, this complex equation can be intuitively simplified into a beautiful, two-beam interference model, the superposition of the front interface reflection beam, which we call R1, and the rear interface reflection beam, R2. The boundary conditions dictate that the interface itself is zero thickness and cannot absorb microwaves. Consequently, the front boundary reflection R1 remains entirely unaffected by the material's attenuation properties. On the other hand, the rear boundary reflection R2 travels through the thickness of the film and back, meaning its amplitude is strongly decayed by the material's attenuation. Therefore, the wave mechanics theory of microwave absorption is elegant because it does not choose between wave interference and material attenuation. Instead, it perfectly integrates both. The phase is dictated by wave propagation and interference, while the amplitude of the second beam is tuned by material decay. When the phase difference between R1 and R2 is 180 degrees, absorption is maximized. When it is 0 degrees, absorption is minimized. Scene 2, the zero absorption benchmark. To prove this mechanism beyond any doubt, let us consider an extreme benchmark. What happens when the material has absolutely zero ability to absorb microwaves? That is, when the imaginary parts of permittivity and permeability are both zero. Under this condition, the overall reflection loss, absolute RL, must be exactly 1 for all film thicknesses. Since the material cannot absorb energy, conservation of energy dictates that whatever enters the film must eventually be returned into free space via the rear boundary reflection R2. But we must make a critical distinction here, one that mainstream scientists often completely confuse. We must distinguish between the total energy returned and the amplitude of the individual split beams. While the total returned energy is equal to the entering energy, energy is not the same as the amplitude of the individual split beams in the infinite ray series. Why can the amplitude of the combined rear boundary reflection R2 be so large at a 180-degree phase difference? If the returned energy has not yet fully met the physical boundary requirements, meaning the entering energy has not yet been entirely spat back out, the internal R2 beam amplitude inside the film cannot be zero. The wave must continue to reflect back and forth within the film until the integrated R2 matches the physical boundary value, and only then does the final remaining beam of the internal R2 series decay to zero. As we proved and plotted in Figure 5 of our 2022 Materials Chemistry and Physics paper. When the phase difference between R1 and R2 is 0 degrees, the two reflections are in phase. Because R1 already reflects some of the incident wave, R2 is at its absolute minimum amplitude. But when the phase difference is 180 degrees, the two beams are out of phase. To satisfy energy conservation and cancel the front reflection R1, the amplitude of R2 must reach its absolute maximum. As the film thickness d increases, the phase difference between R1 and R2 increases. Energy conservation guarantees that from 0 to 180 degrees, the magnitude of R2 increases, and from 180 to 360 degrees, it decreases. This counterintuitive behavior is the direct, undeniable consequence of wave conservation. Scene 3, the absorbing reality. Now, let us introduce reality, a material that does absorb microwaves. When the material has attenuation capacity, a monotonically decreasing factor is superimposed onto the amplitude of R2. As the film thickness d increases, the material's attenuation dampens R2 further and further. Let us trace the reflection loss, absolute RL, as the phase difference increases with thickness. In the range from 0 to 180 degrees, the material attenuation factor dampens R2, and the wave interference effect wants to decrease RL. The combination of these two factors causes absolute RL to plummet, creating an incredibly strong, sharp absorption peak when the phase difference reaches 180 degrees. in the range from 180 to 360 degrees. However, the wave interference effect works in the opposite direction, pushing absolute RL upward, even as the material attenuation continues to decay R2. This is the true, beautiful mechanism of microwave absorption. The absorption peak is not a magic resonance of the material. It is the deterministic result of material attenuation acting as an amplitude decaying factor on top of a wave interference process. Wave mechanics perfectly bridges the gap between atomic decay and physical device boundaries. Scene 4, Cleansing the Vulgar Empiricism. This complete theory represents a profound philosophical departure from the vulgar empiricism or PHOW philosophy that dominates mainstream materials science. Mainstream researchers often treat the fitting of experimental curves as the sole validation of physical truth. If they can fit a reflection loss curve using a flawed model, they declare the model correct, ignoring the logical and mathematical self-contradictions beneath. Consider the history of science. Chemistry was once a collection of mystical, qualitative receipts, the alchemy. It was only when Antoine Lavoisier introduced quantitative mass balance and arithmetic relationships that the phlogiston theory was overthrown. This led to the establishment of the law of definite proportions and the law of multiple proportions, which ultimately paved the way for modern atomic and molecular theory. Lavoisier's quantitative rigor elevated chemistry from the spiritual pursuit of alchemy into a rigorous, predictive branch of modern science. Today, microwave absorption research is in its own pre-scientific, alchemy stage, dominated by the phenomenological fits of the impedance matching theory. Our wave mechanics theory provides the exact quantitative and arithmetic relationships required to elevate this entire field from empirical curve fitting into a true, rigorous branch of modern wave physics. A model that violates energy conservation cannot be rescued by any amount of experimental data. Wave mechanics, by contrast, relies on the ironclad laws of wave propagation. It explains why a film absorbs more than the material can, why the peak moves with thickness, and how energy is conserved under all conditions. To design the next generation of electromagnetic materials, we must abandon phenomenological curve fitting and embrace the true wave mechanics boundary mechanics. Join us on Substack and SSRN to explore the complete mathematical derivations. Thank you for watching.